Welcome to this hybrid event arranged by the IET's Anglian Coastal Local Network, which represents members in North Essex, Norfolk and Suffolk. I'd like to introduce our speaker, Andrew Lord. Andrew joined BT in 1985 and holds a BA in physics from Oxford. He's designed a wide range of optical network systems and technologies, including long-haul subsea and terrestrial DWDM networks. He's been responsible for optical fibre and systems specifications. He currently leads BT's optical research, including optical access, high-speed transmission, and quantum communications. Andrew initiated BT's quantum research with applications in areas such as secure communications, timing and sensing. He regularly speaks at conferences and sits on several organising committees. He is a visiting professor at Essex University, a fellow of the IEEE, and elected one of the first BT fellows. So Andrew, over to you.
Thank you. Really great to be here. There's the people I haven't seen for ages. I'm feeling a bit emotional actually. I'm going to come back to this question at the end. I'm going to ask for a vote. I'm going to try and convince you it's the former. Okay, but please be honest. Clearly I'm biased, but also I'd like to acknowledge a really large number of people, a whole load of people in my team, but a lot of other people you might recognise. That people that have shown leadership where they could have easily said, well, no, we're not doing that. Maybe they should have done, but anyway, leadership means that people like myself get a chance to do some really exciting things. I've got a clicker as well. I'm going to use that. So what I want to do is talk about quantum in general, what we understand by it, because it's a word that's being thrown around and it's being used in this kind of specific way. So I want to be a bit more precise and just look at some of the kind of benefits that are emerging, and then focus particularly on communications. That's what BT does. I'm going to give a very UK but then a global context, because we are not alone and there's a lot of activities going on globally. And just then going to dip into a few things we're doing at the moment as kind of snapshots of projects that we're involved in, just to give you a flavour of some of the people and some of the things we're up to. Then we'll have a vote. So the slide I always start with, and I get my boss, Maria, thinks this is hilarious, but I keep using this one. A train, you can see it, it's obvious it's there, you can measure its speed, measure its location, so you don't kind of question the fact that something might be in two places at once, or might be going at different velocities at the same time, might be spinning up and down at the same time, because trains don't do that kind of thing. So why would anything else do that? That our perception of the world comes from our experience of things that we're used to, like macroscopic objects like this. I can hold it, I can feel it. But when it comes to tiny things like atoms and photons, that's not the case. There's some kind of picture or representation of an atom that's clearly got two centers, two location centers. That's not just because I don't have a very good microscope. It's innate, it's intrinsic. So things that are tiny can have the probability of being in multiple places at once, or go at different speeds at once, or have different spins or different energies at the same time, at least until we look at them. And that's weird. So in the next slide or two, we're going to talk about some of the really weird things that come out of this. But that's the first one. Now that fuzziness, that probability has been known for a long time, but only recently that it's starting to become useful. And the kind of reason why that's useful is I can construct a very secure communication system out of it. If I can send information that is intrinsically fuzzy, then if someone then gets in the way and observes it, they can't help but interact with that fuzziness and change it. Then I've got something that is instantly detectable at the far end. So we're going to spend some time developing that thought. Innately fuzzy things are great for security. but it gets much weirder than that. What if I had two of them? just having two doesn't seem such a big deal, but actually the complexity gets massive. So let's imagine I've got two of those atoms, both of them in two states at once. And I do something between them, which we'll talk about later. And it's not trivial, but I do something that entangles them, that combines them together such that they're both random, they're both fuzzy, but the fuzzinesses, if that's a word, are linked. And that's called entanglement. So here I've got one atom that's could be spinning this way, could be spinning that way. It won't know until you measure it, and then it'll have to decide. And the second or the instant that you look at it, it will have to decide. I'm one of these. Oh, no, I'm one of those. But you can't tell it. It will decide on its own. It's a random thing. Fine. Weird, but fine. Imagine I've got another one, also with those same behavior. But if they're entangled, an instant measurement of this one affects that one. So if I measure this one and it just happens to be like that, that one will be 2. If I measure this one and it just happens to be like that, that one will be down as well. Fine. But that could be at the other side of the universe, or the other side of the country or the world. That could be at the other end of a fibre that's hundreds of kilometers long. And it's instant, and there's no communication between them. They can be intrinsically linked. And that's just the way the universe is. And that should feel weird. Okay, if you think that's normal, you've not understood what I was just saying. it's weird. So we're going to go over this argument 2 or 3 times just to try to kind of play it out a bit. Just a side note. I was at a big conference, science conference, a few years ago, and the lady who was responsible for child education in, I think it was South Korea, it might have been Singapore, gave me a little cartoon book with a little rabbit called Cubit the rabbit, which they give to all of their 6-year-olds to teach them this. I'll just leave that with you. Oh, and so what's it good for? The first thing is an atom that's in 2 places at once. So we're going to call it a qubit. It's representing potentially a 1 and a 0 at the same time. It's not just a bit, it's a quantum bit. And that is really powerful. And we'll come on to why that's such a big deal compared to a bit later. What it means is you can start to make quantum computers. And a quantum computer is simply a whole load of these entangled together. It's like a big array of atoms, all in these fuzzy states, jiggling around, but all entangled with each other. So that you do anything with one of them, they are all instantly affected. Can you at least qualitatively see how fast that is? If I could generate 100 atoms that are all somehow entangled and do something to it, in the knowledge that then all of those other atoms are instantly affected, can you see at least qualitatively that might be really powerful? So that is a quantum computer. Again, we'll come back to it later. I'm just trying to make sure you stay, because now you've got the certificate, you might just want to go and say, yeah, I've done that. Of course, quantum secure communications is the really big one for us, because it's got a lot of repercussions. I'm just going to hammer home what I've said, but this is essentially the same. 2 things that I want you to, if you go away with nothing else. Firstly, if you look at a small object, you will change it. If it's in these 2 states at once before you look at it, it cannot be once you've looked at it. Because if you're looking here, it's either there or it's not. So once you've looked at it, it can't stay fuzzy. But it will be fuzzy until you look. What that means is that you and me are intrinsically involved with the quantum world. Just by looking, you don't think you can just kind of stand off and look and expect nothing to happen. It will change. And that's really useful, because we can actually detect when people are looking at our systems. And then secondly, things can be entangled such that anything can entangle with anything else, irrespective of how far they are away. And this is the basis of the quantum computer and the quantum internet, which we'll come to later. But just to kind of tease out a little bit quite how powerful this is. Let's imagine I've got, let's make Q 100. I've got 100 atoms in a lab, somehow entangled. Each atom can be in a 0 or a 1 state. The total number of states I can then have is 2 to the power 100. Yeah? If I've got one atom, it's in 2 states. 2 atoms are in 4. 3 atoms are in 8. So I can have all those combinations. Type 2 to the power 100 into your calculator, you get an error. Just 100 qubits is already way more powerful than my calculator in my phone or laptop. And we're predicting many, many more qubits than that. So it's the IET. We need to do a little bit of maths, don't we? Don't panic. And actually, this maths is wrong. I told Andy it's wrong, so Andy's going to try and find out where it is. And actually, it's not meant to be precise. But I just want to give you a flavour. And actually, the main message here is the maths in quantum is really simple. If people kind of say, oh, it's very complicated, it's actually not. It's just matrices and vectors. We all know that. So here, so this first thing to notice is this funny line here and this funny arrow. That is a bracket, and it was invented by Paul Dirac because he needed a new way of describing quantum mechanics. All this is a state. So this is a way of saying, defining a state that an atom is in. This atom, its state is up. It's not fuzzy. Okay, I've set it up in a situation where it's just spinning up. This one's spinning down. Simple. But I can make much more complicated things than that. So this one here, this atom here, is in a state where it is half up and half down. In fact, these should be numbers. I put arrows, but actually this should be a number. So this should be a half and a half. I'm trying to keep this really simple. What this is actually measuring is a kind of probability wave on this atom. It's saying this atom, it could be up, it could be down, we don't know yet, but it's in some sense it's a mixture of both. Weird, but still fine. But I can, if you accept that you can just start to write these things down, you can write this down. You can say, I'm going to have a 2 atom state where the first number or the first sign represents the first atom and the second one, the second one. So this state here, I've got 2 atoms, one spinning up, one spinning down. Okay. Now it gets really interesting, and I don't really do anything clever to make it interesting. I'm just going to continue to write equations until something weird happens. What about this one? So here I've got, and this is the mistake actually, this one, I need to reverse these arrows. I did a cut and paste, forgot to switch them. Apologies. You saw that, didn't you, Andy? 2 atoms in every possible combination of states. They could both be up, they could both be down. The first could be up and the second one down, or vice versa, because of the mistake. If I were to look at this system of 2 atoms and say, I'm going to measure one of them, let's say I measure the first one, and I measure it to be up. This is still okay, this is still okay with these 2 spin. So I'm left with this, but the second atom is still possibly up or down. So in other words, a measurement of the first atom hasn't affected the second one. They're independent. All I've done here is just say, I've got 2 atoms that are completely independent. That's all I've done. But why can't I write this one down? And this is the thing that Einstein, as soon as he saw Heisenberg's attempt at writing down quantum mechanics in matrices, thought, hang on a minute, something's weird is going on. I don't like this. Because of things like this. Because what this implies is, if I were to measure atom 1, you notice I've got rid of these 2 states. Let's imagine I can do this. If I was to measure atom 1 like this, instantly atom 2 has to be going the same way because there is no mixed state. Now, just measurement of atom 1, it could either be this or this. So atom 1 could be a completely random measurement. Same for atom 2. It could be a completely random measurement. It's just that once I've measured the first one, the second one is completely determined, or vice versa. Since I measure the second one, I get a result for the first. This is entanglement. It's an entangled state. It's the simplest one you can draw, and it's weird because nothing here says that this atom here has to be next to this one. Nothing. These two could be miles apart. There's nothing in this matrices that says, by the way, these two are talking to each other, or they're linked, or something like that. They're not. So this is weird. Now, quiz, and there's only one quiz, so relax. Once you've got through this one, and this is a test I give to all people that I interview for quantum jobs. Well, at least until one person got quite stressed, and I don't think this is that difficult, but let's see. Just relax. I've got polarized light like this, and it's going through a polarizer at the top. What happens? This is really easy. It's not meant to be hard. How much of the light goes through? All of it. Yay! This guy didn't get that far. He's going, now I know this. I've done this. Okay, same polarized light. This time I'm going to turn the polarizer 90 degrees. What comes through now? Okay. I'm now going to turn the polarizer to 45 degrees. What comes through now? Half. Yes, half in terms of the power. What polarization would it be? It has to be like this. Fine so far. Now the key question, the question that gets you in a job or not. This is no longer a big beam of laser light. It's just one photon. I've reduced this so much that I'm just sending one at a time. What comes through? The top one, it always goes through. The second one, it never goes through. But what about here? Anyone want to be brave? Which half?
The half is aligned to 45.
It is half, and it's completely random. Because at this point, this can be viewed as having two vector states. So if I resolve this like this and this, can you see? I can essentially say this is in two states. One's like this and one's like this. Like this, it goes through. Like this, it doesn't. Whether this photon gets through or not is a decision it makes when it gets measured by this polarizer. And it's random. People are using this to make random number generators, and they're selling them. And random number generators using this technique are the most random things you can get in the universe. Really powerful, really useful things. Okay, I need to speed up a bit because I was getting carried away there. Some of the kind of areas that you might want to think about applications, obviously computing, communications, but you can do other things because these atoms are incredibly sensitive, so you can make them into sensors, and I've got an example later. Incredibly accurate sensor clocks, ridiculously accurate. So the biggest, most accurate clock that we played with is at Birmingham University, and it's down at 10 to the minus 18 of a second. So it drifts by less than 1 second per universe. Overkill, right? Well, not for them because they're measuring things like gravitational waves. So for them, they need that level of timing accuracy. Probably for a 5G network, you might not. Not yet, anyway. Maybe that's 6G or something. Right. Most of the theory done. Let's look about what we've been doing about this. So here is a kind of potted history of when, not actually first contact. First contact was back in '94 with Paul Townsend, now in Ireland, at Tyndall. Developed some QKD over passive optical network systems way back, way ahead of its time. And so far ahead we left it. And the patents, of course, expired. In 2013, we kind of started again. So we've now been going for about 11 years. And you can see some of the things that we've done there, and I'll talk about some of these later. That's me trying to explain quantum physics to Princess Anne. But a minute before that, I called her Your Royal Highness by mistake, or Your Majesty or something, and I don't know, it just went badly wrong. Tim Whitley was fine about it. I just wish I'd looked at the camera. Right, what I'm going to do just for one slide is forget about quantum, because we need some background on cryptography, and then we'll come back to the sexy stuff. Okay, Andy's sitting over there. Andy, I'm going to send you a message and I'm going to get it to you securely. To do that, I need to lock it up. I'm going to lock it with my key, my trusty key, and it gets to you and you need to unlock it, but you need the same key. Otherwise you can't unlock it. So I'm going to get this key to you somehow. So I'm not going to throw it, don't worry. Either I give it to someone and courier it to you, put it in a briefcase or something like that. And it's my car key, so you can't have it. But actually in networks, we have to do something a bit more intelligent than that. And so this is the nub of it. How do I get that secure key from me to Andy? I use another key, but I use a pair of keys. This is the main conversation I want to have for the next 5 minutes. This pair of keys is a pair of a private and a public key. And this dominates all of our finance on the internet. Most of our cryptography uses this technique. So if you don't know about it, you probably should. It uses algorithms such as this, and it works like this. Andy has a private key, and he probably doesn't even know because it will be built into some application software or into his phone or something, but he's not aware of it, but he has a private key, and it has an associated public key with it. They're a pair, they're linked. You can get one from the other. I lock up my symmetric key, right, the key that I'm going to use to encrypt the data. I lock that up with his public key, like anyone could. So anyone can send him information, but that public key doesn't do any unlocking, it just locks. It would be like having a house where you use one key to lock and one to unlock. Only Andy can retrieve the information because he has the private key. Great. This public and private key are directly linked. It's just that to work out the private key from the public one is billions of years on a computer. You have to literally go through them one at a time until you find it. Well, maybe not, not as long as that, but it's a long time. The problem is quantum computers have got a much quicker method of solving that problem. And we're going to look at that on the next slide. A quantum computer using something called Shor's algorithm. This is a very famous algorithm. This has even appeared on Big Bang Theory, so it must be famous. It's an algorithm invented by Professor Shor 20 years ago. Only runs on a quantum computer, which still doesn't really exist. So that is amazing foresight. The algorithm looks something like this, don't worry. But just to give you a feel for what's happening here, we've got qubits. These will be Andy's public key, or the bits of it, and there's probably 1,028 of them. So a typical public key is about that long. 1,028 of these go into what is essentially a quantum Fourier transform, and a few other things. What that does is spews out the private key, and there's a lot more details in there as well, of course, but it's not a big long search process. It's something that can be done in minutes or hours. And of course, once we have a quantum computer with this many qubits, we're in trouble. We have a cryptography system that's flawed. Well, it's worse than that. Let's hack into a system now. I can't decrypt it now, but let's just hack in now and let's wait till I've got a quantum computer. So there is a fundamental issue around public key cryptography, which is very well known worldwide. And there is this timeline of a solution towards it, which you've probably been looking at. NIST set up a competition 7 years ago to try to find a new algorithm, okay, that's better than these ones. And incidentally, these algorithms mainly rely on factorizing a very big number. So essentially, they take the private key and try to find the factors of it. And factorizing a huge, great number of 1,028 bits actually takes a long time. But Shor's algorithm finds that it does factorization really quickly. So you can see basically what's happening here is we've got to a point around now when we have a standard for new algorithms that we believe currently are not susceptible to this or any other quantum problem and any other quantum algorithm. We believe they're not, and of course there might be at some point. And research on breaking these algorithms, as you can imagine, is rife. Everybody wants to get the hero status of being the one that broke the algorithm. So, nevertheless, it's a very valid and necessary approach to keep trying to make harder and harder algorithms. What I want to talk about here, though, is a completely different way of getting that key to Andy, where we don't need to worry about quantum computers or algorithms or anything. And it's this. So instead of getting stuck in maths, I'm now going to send to Andy my key on single photons, one at a time. And these photons are carrying each of them one bit of the key. And I'm going to claim that that's very hard to hack into, if not impossible, for two reasons. And they require the quantum physics that you've already learned. So we should be experts on this. But the obvious thing is, if someone tries to steal this photon here by tapping it off, Andy won't get it. So there's going to be no key there. So he can only make keys out of things he receives. That doesn't need quantum physics. There's no point trying to steal anything. What clever hackers will try and do is just observe this photon, have a look at it, and then let it carry on. But as you should now know, that doesn't work. This photon is a qubit, it's in a fuzzy state, and looking at it changes it. So this photon will arrive at Andy's desk. Someone's looked at this, someone's looked at my photon. And instantly an alarm goes off. So this is an intrinsically hack-free way of distributing keys. Does that make sense? Oh, I explained it well then. I don't normally get it quite as clear as that. But just to hammer it home, I'm going to just try and do it one more time. It's the IET, we need to do a bit of maths. So there's actually a few more details, and I just want to go through them. In order to make use of this fuzziness, what I need to do is send this key to Andy in different basis states. So I'm going to very, very quickly describe it, and it's something, if you're interested, go and look it up. There's a brilliant article on Wikipedia that describes it. But essentially, I'm sending Andy a photon that could be like this, like this, like this, or like this. This is my vertical horizontal basis. These are my 45-degree off-axis basis. And that would be a 1 in this basis. That would be a 1 in this basis. Fine. A hacker doesn't know which basis I'm sending them on, and I just randomize this. Now, if a hacker comes along and says, okay, here's a photon, I'm going to measure it using this basis. And if I had sent it in this basis, one of these in this basis is rubbish, is random, and vice versa. So the hacker has to be able to guess every single time which basis I've sent. But I use a quantum random number generator to determine these. Okay, so I'm sending Andy ones and zeros with random bases, which the hacker can't guess. But what about Andy? How does he guess? He doesn't. He makes his own guess, and we get it wrong. So half the time he'll get the wrong basis. But what we now do is have a conversation. So we have a secure conversation channel, and Andy says, hey, I've got some photons from you, and I measured them in these bases. Do you agree with those? And I'll say, well, this one, no, this one, yeah, this one, no. So we agree, not which photons we measured, but how we measured them. On that basis, we form keys. And okay, I don't want to go over it in much more detail because I could talk for a long time, but hopefully that's enough just to kind of get you interested in how this works. The hacker has no idea, and he can't intercept this conversation because this conversation is already authenticated. Back in 2019, we tried to do a real live demo with the National Competence Centre in Bristol. They do designs of impressive things like aircraft wings, and they want to send these designs, which are secure, to a building that does massive 3D printing of them. And what they were doing is putting them on memory sticks and getting on the bus and going to Bristol. So now they've got a dedicated QKD link to do it. Great, brilliant use case, but it's just point to point. What we've been doing in the last 2 years is trying to see how to extend quantum into a network. Networking brings all kinds of questions. Like, I'm sending keys to Andy, but I'm now sending keys somewhere else. How am I going to kind of organize all of that? For us, once we started building this, we were convinced that the technology worked. what we wanted to do now is, well, two things. Firstly, how easy is it to integrate into BT's network? And secondly, what would people use it for? What are the use cases? What kind of customers would be interested in this? Some details. So we have 3 quantum nodes in London. These are 3 major BT exchanges, 2 in the centre of London, 1 in Slough near the Equinix data centre for potential quantum secure uploads to cloud. And the idea is customers can connect in to an access link and then go on a shared quantum metro network. And I've got some more pictures of that coming up. So this is the customer kind of centric view. So this is our metro network in the middle. This is shared quantum key distribution, where keys from multiple customers go to the right endpoints. Immediately that should ring alarm bells that, hang on a minute, yes, you need a really good key management system to make sure that these keys don't get mixed up. As soon as you build a quantum network, you have to deal with that. This is a dedicated access link. So here it's a dedicated fiber to the customer, same at the other end. We use standard OpenReach optical fiber access to do this, except we're putting quantum over it, not just Ethernet, but it works. And then the keys just end up going all the way through the network, and then you use to encrypt the data at the end. In this case, it's 10 gigabit, but we've had trials at 400 gigs and 800 gigs. So we can do almost any encryption of data using this technique. and some technical details which might be interesting for people that have done a bit of optics. This is the overall kind of system layout. So this is a custom site. We've got 2 metro nodes here and another customer site. The QKD bit is at the bottom, and that's generating single photons at a wavelength. But we want to put that on the same fiber as everything else, because this is a customer access. This is, you know, we can't give them hundreds of wavelengths. So that goes into one wavelength, and it goes into a WDM multiplexer to add colors to the data channels. Key management system gets those keys and feeds them into an encryptor that takes the customer data on another wavelength, different color, and they're added together. So the data and the keys are on the same fiber. It's very efficient. Goes through the network and out the other side. KMS, the key management thing, is an overall kind of orchestrator, and it's really crucial to this whole exercise. This is a slide from HSBC. So HSBC are one of our main customer clients for this network, and they presented this at a big conference. So I'm kind of using it. But what's nice is that they're singing about this, so that's why it's nice to use this slide. And these are some of the use cases that they've been trialing. They've even done a video call that's quantum protected. Now the bandwidth's actually quite limited with QKD in terms of if you want to do real-time encryption with video link. But nevertheless, we had a go at it. But clearly things like financial transactions were really important, as well as just basic customer backup to the cloud. Okay. We have many more plans to extend the work with HSBC in the future. This is really just the beginning. So what is the kind of timeline? Where are we headed? And what do I expect to see next? So this was the point-to-point thing in Bristol. This is where we are now. We're building networks, at least metro networks around a city. The next really big thing that's coming in the next couple of years is satellites are being launched that do single photon transmission to the planet. Honestly, and that might feel like that's unbelievable, but actually the Chinese have been doing this for a while. There are issues with it, but given the new kind of era of thousands of satellite launches into LEO space, people like Elon Musk kind of fueling what's been a massive kind of rise of satellite capability. You can imagine that there would be dozens or even more satellites simultaneously carrying keys and sending keys to the planet. So within a year or two, I expect to see the first trials of that And that is really powerful because combining that with this, I can start to do global security using quantum. Meanwhile, the government, and I'm going to talk about the government in a minute because they have a big part to play, but they're very keen to build their own national service. Yeah, we'll come on to that in a minute. So, those things at the end, I'm going to spend some time on. So. If I was to kind of, in my dreams, I don't get that much, this is what I dream about. Wouldn't this be amazing to have a QKD network that spanned the entire end-to-end network? Well, yes, but you can't really do the same thing here, here, and here, and here. This is a core network which is hundreds of kilometers. This one's about tens of kilometers. This is very, very cheap. Are you seriously proposing quantum to people's homes? Well, I wouldn't seriously propose that, but the conference that I helped lead at OFC earlier this year had at least 3 papers doing this. So I've seen one company designing QKD chips as little pluggables about this size, plug straight into a router that does all of the QKD, costing, I mean, I guess still expensive, but nothing like the cost that we're seeing in this part of the network. So in other words, there are different types of QKD, different types of quantum security, depending whether you're here, 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 or satellite. Clearly, a QKD here has to carry the nation's traffic, and so it's got to be a bigger beast, having more keys. Here, it's got to be kind of cheap and cheerful. Whether we actually ever get consumer QKD, I doubt, but at least businesses on the edge here then could have an end-to-end link, and that I think is really attractive. Now, the government is really keen on this as a kind of end goal. In other words, it's not just about QKD, but there is a convergence between quantum computing and quantum communications. So just bear with me and let me try to unpack this. Let me start from this end. I've got a quantum computer and it's got a certain power. Let's say it's got 50 qubits. So its power, let's call it 2 to the power 50, big number. Let's say someone else comes along and builds another one, this one. Let's say it's also 50 qubits, 2 to the 15. 2 computers here. I've got this another quiz question just thought of. 2 to the 50 and 2 to the 50 in terms of power. Let's say I can connect them together and make a network and use the combined compute resources of these 2 quantum computers. What's the total power? Is it double? I don't think it's double. 2 to the 100. I've got 50 qubits there entangled with 50 qubits here. Effectively, these are now one big distributed computer with 100 qubits. That hasn't gone up by double, that's gone up by 2 to the 50. And I've got another one and another one. Can you see now how the excitement starts to rise when I build a network of quantum computer devices? That the power gets, or the computing power gets almost unimaginable. And I don't think it's just quantum. I think there's going to be lots of conventional compute sitting there as well, with an entangled network connecting them. This, it might be a fiber, but it's not just a fiber carrying regular telecoms. That's not going to work. This has to carry qubits. So there's a huge amount of work going on, including at BT, looking at how do you send qubits over a regular fiber network. So these things are photons, but they're photons that are one at a time in that entangled state with something else. So this photon link here has to entangle this atom array here with this one. So this atom array jiggling around has to generate a photon that is entangled with it. That entangled photon then comes over here and entangles itself with this one, so that the entanglement between these end computers is swapped. It sounds incredible, but that's the vision in the next 10 years to build those kinds of things. And then how would that be used? So I can imagine multiple customers who want to do a very complex optimization, etc. It could be financial, it could be logistics, it could be pharmaceuticals, it could be people trying to optimize a telecom network. They want access to this resource. They might only need it for half a second. Probably that's enough, but how do they get onto it? So you can see how the picture now starts to emerge that ultimately there's a quantum internet. To the government. So this is what they've been saying. They've committed 2.5 billion. That was in the autumn statement. And they've identified 5 missions. In the next slide, I'll show you all those 5, but I want to focus on one of them. This is a 10-year vision, and they want to essentially build the UK's ecosystem in quantum. We have a whole load of small startups. We have a brilliant university system. And we have a few larger players like BT, and the government really wants to try to make sure that the UK is in a strong position to win. Mission 2 is to do this, to build the world's most advanced quantum network by 2035. That thing I've just shown you, they want to build one of those and it to be the best in the next 11 years. I wouldn't say we're ahead, so that's quite a big ambition. Okay, it's a worthwhile ambition. It's not something that is inevitable by any means. And they have all these other ambitions here. They want to see startups develop into SMEs, and they want to see employment and etc. The current status, so exactly where we are at the moment, this is a quite exciting moment because the government is about to announce the next generation of quantum hubs. So these are in the industry, these are known, but they're not announced yet. But this is coming in the next few weeks. These will basically carry on the research to build this, at least in terms of the components that you need, like quantum memories, quantum repeaters, and those things that facilitate quantum entanglement. Another really exciting thing is UK Quantum is an industry body. In fact, those who remember Jonathan Lee Smith at BT, he's now head of UK Quantum, doing a fantastic job, essentially representing what is still a fragile quantum industry for the UK. We have an ecosystem. These are the other missions if you're interested, and there's some really interesting ones. For example, here, quantum sensing on your brain is a very non-invasive way of measuring brain waves without you having to have massive great scans and things that affect, So I think something like this for children would be a brilliant way of doing brain scans. There's other things like putting quantum navigation into aircraft, so you don't need to rely on GPS, that kind of thing. But go and have a look at it, because there's 40-50 pages of very interesting stuff there. But we're not alone. So this should bring us all back to earth. The Chinese clearly have been working very hard in the area, and they have a very impressive quantum system. It's been there for a while. They've built quantum satellites as well. South Korea have a real QKD secured 5G backhaul link. They even bought a QKD vendor. They're so keen on it. Europe is building 18 separate national quantum networks. The UK is frozen out of this by Brexit. Brexit hasn't stopped the UK and the EU collaborating, except in areas where the EU thinks it's really important to keep stuff, and quantum is one of those. But that's a shame. But anyway, we observing what they're building in Europe, there's 18 separate quantum networks that will ultimately be linked together. Singapore as well. Okay, I'm coming near to the end. I just want to very quickly give you a flavour of the kind of projects we're doing. This one is a project we led, just finished, looking at doing QKD over free space. So the ambition here is to do things like autonomous vehicle connectivity securely using quantum, or connecting lampposts and things, and it worked really well. This one is about how do we what does a data center look like when it's got quantum in it? And we had a brilliant demo at Industrial Park a few months ago, where we had the first time we got a quantum computer in a Dastor. We just got it in the lift. Literally, there was about an inch to spare to get it up into the hothouse if you know Dastor. So that was a very exciting demo. But the serious aspect here is ultimately these computers are going to be in data centers. They're going to be doing stuff. So how does that architecture work? What does that future hybrid data center look like? And kind of thrilling thing here that's hit the news recently, and this is not my team, this is a team led by Dan Gilks, have put a atom into a cell, excited it to what we call a Rydberg state. So this is where the electrons almost escape, but not quite. And these energy levels here are radio-like So radio waves now can be detected by these cells. This is now a new radio antenna with no metal, way more sensitive than metal antennas. So yeah, this is a brilliant way to to try to make use of this technology. And what I want to do just at the very end is to talk about quantum computers. Now, what I suggest the IET gets someone else in, probably Kathy White, who works for me, to talk about quantum computers all night. And so I don't propose to do that. But honestly, these are the things they're the big ticket item. These are the sexy thing that is going to drive all of this. And here is a project that is coming to an end. We've been involved in called Viscity, which is essentially saying, what do I do with quantum computers when they're not perfect? And currently, quantum computers are a bit noisy. They don't work very well. You can entangle, but the entanglement kind of evaporates. It's like this cup of coffee here has got cold. That's what happens to entanglement. You can hold it for maybe half a second and then it's gone. But do we have to wait until all of our computers are better, or can we do things now? And there's a big categorization of the kinds of things that we can do with noisy quantum computers. And a lot of this is to do with optimization of different types of things, whether it's actual physical layer optimization, placing of equipment, all the way down to big, operator optimization of things like field force. Where do I put my open reach vans? Where do I put buildings and things like that? Quantum computers are really good at taking a large number of bits and finding solutions to things like NP-complete problems. So I've got one more slide after this. That's our vote. But quantum is coming. There's no doubt about that. And I've gone through the different areas. But honestly, the quantum computer is the big one because that is promising not only vast compute power, but also it brings in this risk of breaking our current cryptography. For BT and for me, clearly this is interesting because this is how our network might evolve in the future. And we see these two things coming together, computers and communications, into an ultimate quantum network. And there's lots of other things which we're less involved with. But there's an elephant in the room, because a lot of people will say when I do this presentation, yeah, but there's no quantum computer. I can't see one. How do we know it's ever going to happen? You're always saying it's 5 years away. And so therefore, there's a sense of complacency, or just kind of, I'm just going to wait. And there's two things I want to say. The first thing is, it's a massive engineering challenge to build one of those, but no one is aware of any physics that stops it. The physics of entanglement works. There's no reason, in physics why you can't build this. It's just hard in terms of engineering. And the second thing is, we're seeing billions and billions being invested by nation states, by the Americans, the Chinese, and by big companies like IBM and Google. So it's a big engineering challenge with lots of investment. So I'm going to ask you, what do you think? Do you think, from what I've said, is this a game changer, or do you think in the end it's just going to be, a niche thing for the very rich to solve problems that we're not really that bothered about? And honestly, that is a very valid position to take, and people do take that position. So hands up if you think this is a game changer. Yeah, I did it. And hands up if you think it's niche. Who's brave? Well done. Clearly unbiased. Thank you very much. Any questions?
Thank you very much. Thank you, Andrew. That was absolutely great talk. A lot of food for thought there. Those of you online, if you'd like to think about questions, we'll try and pick the questions off from yourselves. But we'll try and alternate, take a question from the room here at the atrium and then one online. So let me open it up. Who's got a question from the atrium?
Thank you. Fascinating talk, very insightful. One of the key challenges must be to manage this entanglement, because for this to work, the photons have to be reliably entangled. Is that a challenge because you're looking at perhaps 100 or hundreds of photons that are entangled?
You have what's called a time stamper, and this thing sits clocking. So every time an entangled photon pair is produced, it registers, and you're telling the far end, expect one now. And actually, the way you detect these things, because detectors of single photons are pretty difficult, is you tend to keep the photon detector shut, and you just open it when you're expecting a photon to come along. So you have the time tagger is essentially synchronized with your detector, saying, oh, there's one coming now, and it measures it or it doesn't. So yeah, it's a very complex kind of synchronization network to keep all this working. Is that what you meant? No.
Possibly. Yeah, I think because you were explaining that I'd always understood it was pairs of photons, but I think you were saying you could have a large number of photons all entangled together.
Right. And so for a computer, you might have lots of atoms all entangled.
Right.
Generally, for communications, you might just use 2 photons. Now, you can entangle more than that for sure, but most of the kind of the simple entanglement in terms of communications that we're looking at, it's just 2. But yeah, you can entangle more photons as well. Yeah.
Right.
It could be n. Yeah.
Okay, thank you, Andrew. Let's take one from online. There's a question here from Tom, and he says, what's your opinion of Robert Lanza's biocentric view of the quantum world in regard to consciousness creating the universe?
So there's a lot of interesting discussion around that, looking at Roger Penrose as well, who has a theory that the mind and decisions and thoughts that are made actually have a quantum origin. So the synapses in the brain, if you drill down to the chemistry of them, there's something quantum that's providing that consciousness, that randomness. I think, and I'm not a biochemist at all, but my understanding is that that's not the received view. That it would be nice to think that somehow quantum is in our brains and it's the thing that causes consciousness, but I think that's still seen as very much unconventional.
Thank you, Andrew. Another question from the room? Tony?
You send one of the entangled pair across your network. Doesn't the network conspire to stop it being coherent and so therefore bullying?
Right. So firstly, the QKD we're doing is not entanglement. So I should have made that clear. So the QKD that I'm sending to Andy is just 1 photon. It's not entangled with anything. I'm doing a very basic use.
Okay, so you said that, didn't you?
Yeah. But more future versions of QKD use entanglement. And why? It gives you bigger distance. So I could have, for example, a node here, and I can send entangled photons that way and that way. And that way I get keys from there to there, and it doubles the distance. So entanglement brings us various benefits in the future as well. But yeah, most of what I've been talking here about is not entanglement.
We'll take another question from here in the atrium. The gentleman over there is first.
Yeah, Colin Blanchard, I used to be at BT. I think in 2003, I got a series of patents to review for applicability of the policy. And it was from the 1994 patent from Simon Phoenix for project key distribution using the language. And I looked at it and thought, well, the question I was asked, can we use this in the mobile network? And it was still sort of PCM, a bit linked, it wasn't optical or anything. And I couldn't see it going on handsets. So that was 2003. If I'd said yes, we knew it for 10 years. So the first question is, would we have been able to keep it in force? The second part of it is, the Starlink, I can now see sending laser beams up to satellites directly, where you've got no protocol conversion or whatever it is, so you get the same quantum preserved the entanglement maybe, and then sending down for reflective coating on the satellite, so you've got direct link. There are people actually implementing something like that now. And would have that taken us to 2033 if somebody had looked back?
So the first question, the patent in 1994 was really clever, and it was using PON, passive optical splitter, and it was sending photons, key photons, QKD photons, into the splitter, and then of course they had 32 ways to go, and they would randomly choose one of those routes. That's the essence of the patent. Brilliant. And it's only going to be, would only be useful if we were to put QKD over PON. It doesn't work with non-optical radio frequencies. Yeah, as soon as you come away from the as soon as you come away from optical frequencies, this whole thing fails because the size of the photon gets too small and it gets swamped with shock noise. So you're in a regime where you just can't detect a single photon. It's kind of meaningless. It's this big thing that's swamped by noise. So unfortunately, I think you probably did the right thing. I mean,
yeah, I was spending too much on it. The guy asked me to do it. He said, "Get on with it, get on with it." And I said, "This is a new field to me. I'm learning."
And I think if it had been the fundamental QKD pattern, then that would be different. But I don't think it was. I think it was a kind of derived on that. Starlink is clearly not doing QKD, but the Chinese are. So the Chinese already have satellites that will send 2 photons to the planet that are entangled, and those 2 photons have to both be detected by different ground stations at the same time, and that way the satellite is untrusted. It's just spewing out entangled photons. But what you get is a key between these 2 points. Really tough because you need no clouds, and you have to get the angles right. That's doable.
Thank you, Andrew. Let's take a question online. Got a question from Alexandros. What kind of software does Quantum Networks require, and how this might change over time?
Okay, hello Alex, nice to see you. I hope Greece is nice. Alex asked this because he's writing some of that software, so
Oh, right.
maybe I should advertise his company at the moment. There's 2 distinct types though. There's the software that is very close to the quantum device, that is essentially managing the APIs that come from it to, for instance, do the key management. And then you've got software that's actually across the whole network doing the orchestration and the SDN. And the 2 need to work together. So you've got kind of component oriented software speaking to the kind of broader one. How I think it will develop is we're going to need a global software control of key distribution, which is going across domains. So it won't all be BT, it'll be BT, and it's like the old telephone network. We'll have to manage international telephone calls. How do you do that when you're distributing keys? I think is unsolved. And so somehow that software is going to have to keep domains of trust in a global environment.
Thank you, Andrew. Let's take another question from the atrium. Maybe over the corner.
Oh, yeah. Thanks, Tony. Great conversation, great lecture, Andrew. My question is mainly about you've got a slide on the data center. What is the difference in terms of data center footprint and a compute where you're doing QKD and then scaling up to this sort of entanglement, kind of more advanced option? Is anyone?
So how I view the data center is there's 2 things. Firstly, it's going to have quantum compute in it, and that is an intra data center question of how you do that, which could use all kinds of things. Could use entanglement, but people wanting to make use of that are going to want probably to put in requests that are secure. So a QKD based query going into a quantum data center is quite important as well. So we're kind of separating it into 2. Where the data center is probably going to be an environment with multiple quantum computers because they'll be close to cooling and they'll share some infrastructure. And what that local area quantum network looks like could be very different from how a consumer or customer kind of gets onto it via more conventional QKD. But we don't really know. So this is research. So these architectures are still being thought through.
Thank you, Andrew. Johnny, you have a question?
I think you said, if I heard you correctly, you've got a quantum computer there. What's the scale of that? And I guess how many qubits have we got to so far in terms of?
Okay, that's 2 questions. So this was just for a demo. It was from a company called Orca. So Orca are a British company that make quantum computers using a very different technique, not atoms, but photons. And I don't want to go into the details of how that's different. But it does mean that it's a smaller, less kind of intrusive device. Probably more limited in terms of what it can do. But anyway, we're working very closely with Orca. In terms of, but it's not really doing qubits. It's a slightly different way of thinking about quantum computing. The more conventional so-called gate-based computers, which are essentially doing XORs and gates and switching, and in the way that conventional computers are, that use atoms. I think we're up to 100 and something. I think IBM, Google, I don't know the latest, but they're in the hundreds of qubits at the moment. The issue being that that entanglement is not that reliable. It doesn't last for very long. And so if you were to do a procedure between two qubits, you wouldn't reliably get the right answer. Whereas if I take two bits and do an exclusive OR, my computer will always get that right. A quantum computer doesn't, because it's just noisy. And so what's developing at the moment is a whole load of quantum noise-tolerant quantum computing, which can cope with the fact that when you do an operation on a quantum computer, it doesn't always give you the same answer. And that uses a whole load more qubits. So there's a vast numbers of qubits just sitting there making sure that you get something right. It's like an error correction sitting on top. What we really need is the fidelity of those gates to improve. But at the moment, what this project that I showed earlier is saying is, well, let's not wait. Let's try and do something useful with it at the moment.
Thank you, Andrew.
Can I also can you get back to the slide on with the receiver? I was just curious. Just look at a few seconds more. If you don't mind. Yeah, thank you.
So let's take a question from online then. We've got a question from, apologies to the requester, I'll just probably read out the surname, Lansdowne Bridge. One thing I missed was how do we store information in qubits and then extract it without making them revert to a 0 or 1 state?
So quantum memory is a thing. It's difficult, and at the moment it's ephemeral, so it doesn't last very long, but you can use an atom to hold a qubit for a short period. That whole science and research into quantum memories is massive. But actually, you can do a lot by just having short-term memory. So you don't necessarily need to hold something for hours. And I think they can hold these entangled states for minutes or so now. I mean, these are incredibly cold. So they're cooled down to almost absolute 0. So there's nothing from the outside getting in. There's no thermal kind of stuff messing it up. So yeah, very, very careful conditions. There's no light, it's all black. And in those situations, you can kind of hold states for several minutes.
Thank you. Thank you, Andrew. We have another question from the audience.
Yeah, so when you talk about plasmids, you mentioned electrons, but when you send a light, first of all, are you entangling the light as a particle? You mentioned sending one single photon. Are you entangling the photon as a particle or a photon as a wavelength?
I mean, it's difficult to use those analogies. What you very simply can think of that photon as a wave until you've measured it, and the wave is kind of somehow representing the different states that it might be in. But when you put it into a single photon detector, it's a photon, and it's either one of those or the other. So that wave function kind of collapses into one state. But the other thing that's I was trying to get across is if I want to connect two quantum computers, one of them, they're probably atom-based. So there's an atom here that wants to communicate, wants to entangle with another atom, but they're over there. So I have to build a quantum link, and that quantum link is probably a fiber with some photons. So somehow I need something that couples an atom, entangles an atom with a photon, sends the photon, and then entangles that photon again with that other atom. That's a really complicated process that's being researched.
Thank you, Andrew.
Did you?
Yeah, that's fine, thank you.
Okay.
One more question online from Colin. And Colin says, thanks for the presentation. Is quantum safe cryptography a viable alternative to QKD?
Absolutely, and we are advocating using both. Quantum safe cryptography or post-quantum cryptography probably is going to be everywhere. There are now plans in place, evolution plans to go from where we are at the moment with public key crypto to PQC. Probably going to take 5 or more years. There are situations where you might want to do both. But yeah, absolutely, it's the de facto way to go about doing this, and it's the recommended way from the National Cybersecurity Centre, and it's something we, absolutely everyone will be using. It'll be on your phone in the future. It's just that niggling doubt that is it completely safe, and if you can do something that's different, why wouldn't you do that as well? And there's some situations where you might want to, bolt the door and the windows and everything.
Thank you, Andrew. Any more questions from the audience?
One very quick one. Is anyone betting on Bitcoin to collapse on the basis that all the people stored it up, forgotten about it, now worthless because they signed?
I'm not going to comment on Bitcoin. I will say that there's a lot of work on quantum fueled AI. So AI clearly is a massive thing, and adding quantum computers to it can do more powerful things with it, or maybe get it to settle on states more quickly. So quantum computers are often one benefit is seen as getting the regular computer to a point where it's close, and then getting that computer to stabilize. As far as Bitcoin's concerned, no idea. I don't own any. Maybe that's a statement.
Thanks, Andrew. Just looking online, we've got a kind of comment from Catherine White. Some current records for number of qubits in a gate. QC IBM Osprey 433 qubits, solid state base. Condor 1121 qubits. But it's not just about the number of qubits, as Andrew said. It's all about the quality, fidelity, and coherence across circuit width and depth, brackets time.
Alfred, can I suggest you get Kathy to do the next talk?
Thank you.
Highly suggestive.
Right.
Thanks, Kathy.
No more questions online. Any more questions from the atrium?
Andrew, thank you for that. That was fascinating. But I'm on slide 2, I think it is. At the bottom, when we talk about entanglement and you can use entanglement. But if I understood you correctly, you said that when atoms are entangled or photons are entangled, you don't know what state one's in until you measure it, and the other one automatically goes into a state. And I think I heard you saying that there's no communication involved, there's no information exchange. So what's going on? You said it was weird and the universe ends, which is fine, but something's happening.
Nothing's happening. It's just the way the universe is. What you can't do, and what normally I get asked this at some point. Why can't I use that to do an instantaneous communication system? Why can't I now transmit to Andy faster than the speed of light? But I can't, because I can't tell this entangled photon here what to be. It just is what it is. So there's no. The reason people worry about this is they're thinking somehow information is going between here. No information is being passed. It just stops short of information. It's something, but it's not information. So Einstein's happy. There's no relativity being broken. And so it's weird, but it's not breaking anything else that we might worry about. So I think that is the concern, is you think, oh, something here, I ought to be able to use this to send some secret message quicker than the speed of light. You can't. It's not information, but it's not quite, nearly.
Any more questions?
Just one more. You mentioned about the quantum computing being noisy, and just in my head, I'm thinking, is that to do with the fact that the entanglement is lost over time? So, I mean, to me, if you've lost that entanglement, then there's an error, and that seems like noise. I mean, is that?
Yeah, the entanglement evaporates. I use the analogy of my coffee. So the entanglement is just evaporating into the atmosphere, or let's be more precise, the atmosphere has got stuff in it that is interacting, and essentially making an observation of, so it's taking that entanglement away. Now imagine I've got 100 of these atoms and they're all entangled, and I want to do some complex process where I'm not just doing two, but I'm somehow doing multiple stages of processing. Each time one of those is slightly noisy, it cascades and gets worse and worse. So a gate fidelity of 99.9%, you might think that's fine, but it's not when you start to do more complicated algorithms.
And that noise is the loss of entanglement.
Yes. Yeah, I think so. Yeah.
Right. I think it's 8:15, and I think we'd like to thank Andrew for a fantastic presentation, and thank you for taking so many questions online and in the atrium. Please join me in thanking Andrew. Andrew, I'd be very grateful if you could just flick on to the last slide. It's my tailing slide. Whilst you're doing that, I'd also like to register my thanks to Afolabi, who put in a lot of work to set this presentation up and did all the organising. Thank you very much on behalf of the IET. And it falls to me to just to plug our next couple or three events. Our next event is a visit to BT's Robotics and Drone Lab. That's on the 5th of June. That's an evening visit to Astral Park, and the registration for that will be up fairly soon. The next one is a presentation by Professor Andy Sutton, again BT Fellow and Principal Network Architect, and Andy's going to be talking about New Space, the Future of Satellite Communications. That's the 18th of July. And another thing which we're really keen on is to make sure everyone knows the routes to registration, and Afolabi will be setting up an IET registration and standards presentation on the 26th of September. We are continually adding to the program, so do have a look at our NGEX site. The link is at the top of the slide here for more information, and that's where you can find the CPD certificate for today's talk by Andrew. And I think that brings us to an end. Once again, Andrew, thank you very much for the work you've put in, and my thanks to the University of Suffolk for the facilities. So we'll draw the meeting to a close. Thank you very much.